Welcome to Discrete Mathematics. Today, we are diving into a fascinating and highly structured topic called complemented lattices. We will explore how mathematical systems can have perfect opposites and why this simple but powerful idea is the absolute foundation of every computer processor in the world. Let us get started. To understand what a complemented lattice is, imagine you are packing for a trip. You have a master checklist of everything you need. If you pack a few items, the complement of your packed bag is exactly the list of items you left behind. When you combine what you packed with what you left behind, you get the complete master checklist. And if you look at what is in both groups at the same time, you find absolutely nothing. This idea of having a perfect opposite that completes the whole without any overlap is the heart of a complemented lattice. Before we can formally define a complemented lattice, we must first understand what a bounded lattice is. Think of a bounded lattice as a structured system that has a clear ceiling and a clear floor. It has a top element, usually written as 1, which represents absolutely everything in the system. It also has a bottom element, written as 0, which represents absolutely nothing. For any element to have a perfect opposite or complement, we need these boundaries to exist, so we know exactly what everything and nothing mean in our specific system. Now that we understand the boundaries, let us look at the mathematical notation for this system. A bounded lattice is represented by the equation L equals the tuple S join meet 0 and 1. Here, S is the set of all elements inside the lattice. The join operator acts much like a union, finding the smallest element greater than both inputs. The meet operator acts like an intersection, finding the largest element smaller than both inputs. Finally, 0 is our absolute bottom element and 1 is our absolute top element. Understanding these symbols is the first step to mastering the structure. This brings us to the first mathematical condition for two elements to be complements. The formula states that the join of element A and element B must equal the top element, 1. Conceptually, this means that if you combine the properties or contents of A and B, you get absolutely everything available in the entire system. If element A gets smaller and holds less information, its complement B must physically get larger to ensure they still combine to make the complete top element. This guarantees that no piece of the whole can ever be left unaccounted for. The second crucial condition for complements is the meet condition. This equation states that the meet of element A and element B must equal the bottom element, 0. In plain English, this means that A and B share absolutely nothing in common except the absolute minimum baseline of the system. If both the join condition and this meet condition hold true at the same time, then B is the true complement of A. If every single element in the lattice has such a partner, the entire structure is officially a complemented lattice, perfectly balanced from top to bottom. Let us see this in action with a classic example from set theory, the power set lattice. Consider a set X containing elements X and Y. The power set S is the set of all possible subsets. To prove this forms a complemented lattice, we first identify our boundaries. The top element, 1, is the entire set X, Y, because no subset can be larger than the original set. The bottom element, 0, is the empty set because it contains absolutely nothing. Now let us test if the elements inside have complements. Continuing with our power set, let us test the subsets containing just X and just Y. We need to see if they satisfy the two complement equations. First, we check the join operation, which in this context is the set union. If we take the element containing X and join it with the element containing Y, we get the full set containing both X and Y. This resulting set is exactly our top element, 1. So the first crucial condition is successfully met. They combine to form the absolute maximum of the system. Now we must check the second condition using the meet operation, which is the set intersection. If we take the intersection of the subset containing X and the subset containing Y, we find they share absolutely no elements. This results in the empty set, which is exactly our bottom element, 0. Since they combine to make the top and overlap to make the bottom, the subset containing Y is the perfect complement of the subset containing X. This proves that our power set is indeed a complemented lattice. To make this even clearer, let us look at the visual representation of our power set lattice, known as a Hasse diagram. At the very bottom, you see the empty set, representing our 0 element. At the very top is the full set, representing our 1 element. On the left and right are our single element subsets. If you trace the paths upward, combining the left and right nodes pushes you to the top. Finding their common ground pulls you down to the bottom. This elegant diamond shape is the classic visual signature of a simple complemented lattice. Now that we have seen sets, let us apply this to number theory with the lattice of divisors for the number 30. Our set includes all positive numbers that divide evenly into 30. Here, the join operation is the least common multiple, and the meet operation is the greatest common divisor. First, we establish our boundaries. The top element is 30 because it is a multiple of every number in our set. The bottom element is 1 because 1 divides evenly into every single number. Let us find the complement for the element 2. We will test the element 15 as a potential complement for the element 2. We start with the join operation, which is the least common multiple. We ask ourselves, what is the smallest number that both 2 and 15 divide into evenly? The answer is 30. Since 30 is our top element, or our 1 in this lattice, the first condition for being a complement is successfully met. The two numbers combine through their least common multiple to reach the absolute ceiling of our divisibility structure. Finally, we check the meet operation, which is the greatest common divisor. We need to find the largest number that divides evenly into both 2 and 15. The only common factor they share is 1. Since 1 is our bottom element or our 0 in this lattice, the second condition is also met. Because their least common multiple is the top element and their greatest common divisor is the bottom element, 15 is the perfect complement to 2. This shows how beautifully lattices apply to numbers. You might be wondering why we care so much about complemented lattices. The answer is that they are the absolute foundation of computer science and digital logic. Every computer processor in the world is built using logic gates that operate on a specific type of complemented lattice called a Boolean algebra. In a computer, the top element is a high voltage representing true and the bottom element is a low voltage representing false. Because every logical statement has a perfect opposite, we can build reliable switching circuits and memory chips. Let us summarize the key takeaways from our exploration today. First, a complemented lattice is a bounded system where every element has a perfect opposite. Second, this opposite or complement must combine with the element to form the absolute maximum and overlap to form the absolute minimum. Finally, this simple but powerful mathematical guarantee is what allows us to break down complex systems into manageable opposing parts, forming the mathematical heartbeat of all modern digital electronics. You have now mastered the fundamentals of complemented lattices.